right, we're going to start our webinar for today. Again, welcome to anybody that's just joined us for our talk today on Project Eureka and adaptive computing at scale. We have Boyd Wilson from Omni Bond here, and Boyd's going to start off with some introductions. And yes, I can enable video. Just a second.
Okay, can you see the slides okay?
Yes.
Oh, perfect. So I'm going to go ahead and begin.
Yes, please. Thank you.
Okay, excellent. I'd like to thank everyone for joining us today. I'm real excited for this opportunity to spend a little time talking about what's up in the cloud for this class presentation series of Internet 2. I'm going to spend a little bit of time going over cloud resources, a cloud of resources, and then spend a little time at the end on Project Eureka, adaptable cyber infrastructure at scale. And there's my connection information. Please feel free to connect LinkedIn, Twitter, Instagram, any of those. Love to connect with people and get feedback. Just a little bit of background on OmniBond. OmniBond is actually a spinoff of Clemson University, and the leadership team has had quite a bit of experience with various different aspects of research computing and educational, IT leadership. And so, we've always been focused and still are focused in helping out communities in this area. OmniBond spun off of Clemson. It originally was in the identity and security management space, originally with Novell, Micro Focus, and now OpenText, doing identity management drivers. And more recently, in this space, we've become an Internet 2 catalyst, and we are working on passwordless MFA with Omni Passkey for federations using Shibboleth. We also do some work in computer vision and AI, more of a real-time HPC problem, where we take existing cameras and turn them into sensors for data incident detection to make roads safer. And we'll be spending time today talking about, cloud HPC and storage orchestration. We've had a previous product called Cloudy Cluster, and we also are maintainers of OrangeFS upstream of the Linux kernel. But the main thing we'll be talking about later on is Project Eureka after we go through the overview. So that's kind of an overview of what we do. So as we evolve in this AI generation, oil, I like to say data is the oil that we're all facing, that helps build and generate all the things of the future. So one of the things I wanted to spend a little time on is kind of just talking about the ecosystem. And so one of the things that, drives everything is data. And so I found this slide from NSF. And, as you go look through these and Google some of these various different projects, there's hundreds of petabytes a year generated just from NSF, and DOE and other places have that, and companies and just us as individuals, generate, petabytes upon petabytes of data. And, being able to do this is, do things with that data, as we've learned over the years, is a double-edged sword, but there's many advancements coming, and it's pretty interesting and pretty exciting as we progress in this space. And for scientific data specifically, where you get the hundreds of petabytes, it goes from sensor networks to satellite imagery to all kinds of really cool stuff. And now we're finally, with AI, starting to be able to pull that data together. And here's another example, weather stations. And we spend a lot of time trying to predict and determine weather patterns and historical temperature and those types of things to really understand the world we live in. Now, with all that data, over the years, we've developed a cloud of cyber infrastructure resources. And a lot of that, the cyber infrastructure CI resources are built upon the Internet 2 network. And I kind of pulled a couple infographics here to kind of see the coverage of the network, but also, down in the left corner, you could see it's 400 gig, zero congestion, 700 petabytes of network traffic daily, almost 16,000 miles of fiber. So it's a vast network to really build as a foundation of these cyber infrastructure resources. And in the research and education community, there's lots of campus locations, and you can kind of see the overlap where these connect and go to RENs, and then you have all the campuses. And you can see there's a wide variety of them all over. And one of the things after you have the network, you need to have resources to compute. So a lot of these campuses actually have computational resources that are available on their campus that they build out for researchers, in different models. There's condominium models. Sometimes there's a big enough project, they have their own clusters. So it's really this vast network pulled together. And just to kind of give a couple of examples, I searched and found some universities and reached out to a couple of people, and a selection of three campuses, Clemson, Princeton, and Oklahoma. You have a varying number of nodes, and then the cores, vast number of cores, and then a varying number of GPUs, which seem to be the refining that we do with our data now is the GPUs for the AI models, but also for the other work that's done. And there's a lot of cores out there, and there's a reason. A lot of work is still done on cores. Even a lot of the inference can be done on kind of standard x64 cores. And there's a lot of storage at just these locations. And if you go back and look at all these locations, many of those locations have systems that look like this, at least the R1s into the R2s. And to layer on top of that capability, there's a lot of NSF cyber infrastructure resources. And if you can kind of look at all the different systems that are available to support, from Fabric to Cloud Bank and integrating cloud to Path and OSG for high throughput computing, to Stampede or Bridges, or any of these other resources are all available and freely available within allocation. We'll talk about that in a little bit. So there's another layer of resources on top of the campus that are all available. And here's a sampling of those resources, number of nodes. Jetstream is more classical, kind of cloud-like, spin up your own resources. Stampede and Bridges, again, is more HPC focused. And you can see a number of cores and GPUs and storage as well. And a lot of these places have multiple of those, again, across these various sites. And to layer on top of that, for several years now, we've had public cloud. And here's a global map of the public cloud provider locations. And you can see that the public cloud has options as well. It's more, spin up your own resources, do those types of things, unless submit a job. You have to do a little work before you can submit jobs if that's what your workload requires. And so, and even, with our previous product, Cloudy Cluster, we've actually done some scaling, and these are high throughput jobs where we have 1.1 million vCPUs, running in spot instances in AWS to work on some NLP type of work, the predecessor to the LLMs. And then we've also done some scaling in Google Cloud, using more sensor data from cameras for processing video incidents with our traffic vision product. And, we spun up to 2.1 million vCPUs. Again, a high throughput workload. There's some cost and there's some numbers, and we'll share these slides at the end. But the cloud is good at scaling certain types of workloads. Each one of those things that we've gone through has their benefits and advantages. But when you're looking at, as your research researcher or as a campus research support person, you really have a complex problem of offerings to let people know what's out there, what's available, and even direct them. So I want to spend a little bit of time just going over the way to access some of these resources. And so there's access, which is kind of the HPC, a lot of HPC clusters that are available through kind of unified authentication system. And you can go to allocation access CCI and see the resources. And that's kind of more your traditional HPC workloads. Low latency interconnects, can do MPI type jobs and those types of things. OSG pool is more high throughput, and there you can get more information at the osghtc.org. And it's where you have individual jobs that need to run and need 8 or less cores, and you using some dedicated space, but also some just extra resources available at some of the, the traditional HPC places as well, and others. NRP, which is focused specifically on Kubernetes, and it's really a Kubernetes hypercluster for containers. So if your workload fits that model, you can look at the NRP, and there's the information, nationalresearchplatform.org, and go look at how to use those resources. Again, all of these are free. There's allocation processes that you can step through on all of those and request allocations. So when you look at some of the cloud offerings, there's various different things. Now, the clouds are, you build your own environment. So you have to, if you want to do HPC, you have to build it some way. And so AWS, to build an HPC cluster, they recommend using FSx for Lustre for storage and Parallel Cluster to kind of spin up those computational resources. Now, Amazon FSx for Lustre, you can spin up, and when you move into this realm, remember the public cloud has costs associated with, so make sure you look at the costs and make sure your funding sources can support these. And the other options above have allocation models, which are free. You just have to request based on allocation. And so you could spin up the storage system, choose what you want, and then you can spin up Parallel Cluster, and there's a command line setup, and then there's also a UI that gives you some information. And I kind of put some links in there, and when you get the presentation, you can click on these and go read how to do it. And there's several steps. You go through the console, and each of these clouds are the same, and you type in some commands and spin it up, and then you get the resources spinning, essentially a login node and a scheduler node. And AWS supports a variety of instance types, x64, GPU, ARM. They support placement policies to get your nodes close together. And if you want to go crazy on network, was a ton of network connections in a single node for a certain type that you can actually spin up and get a lot of throughput. But you don't have the InfiniBand or that low latency, but the networks for these cloud providers are a little lower latency than just your standard Ethernet. And AWS also provides partner solutions if you go to their marketplace, and they have some other things. So, Clouded Cluster, our former product. There's Alsys Flight. There's Ronin, which is really a user-based UI for Parallel Cluster in the HPC space. And then they also have a research and engineering studio, and it's by AWS, that allows you to kind of do remote virtual desktops and those types of things. So this is kind of a quick overview of AWS. And from the Google Cloud perspective, their HPC options, they focus both on their Cloud HPC toolkit, which allows you to develop HPC blueprints for various different types of clusters, and then it generates Terraform scripts for that, so you can spin up using Terraform, and it actually even launches the Terraform. And you can kind of see clone the repository, build the binary, complete a deployment folder, put the stuff in there, and then spin off. And then, in one configuration, you can actually have a Slurm cluster that uses the power on-off feature to launch HPC instances based on the type on a partition basis or queue basis. Google also highlights several partner options on their HPC page, and we're listed as one of them, but there are several others that are available. And Google Cloud supports a variety of instance types, x64 GPU, ARM, TPU. And the one thing the cloud provides is the ability to have a lot of new technology available for you very quickly. So you can spin up and do those things. And they have, really fast network, not as low latency as InfiniBand. But again, a good option for the cloud. Now, in the Azure space, for their HPC resource options, kind of reviewing their website and the documentation and the GitHub, they really focus on Azure Cycle Cloud, which is someone they acquired many years ago. And again, there's a doc links and how you can create the VM from the Cycle Cloud image. And they give you a UI to spin up the image. And then you can move on to, and there's kind of an architecture of how they have an API and they have agents that plug into the different schedulers that you can use. Generally people use, can use Slurm or various other options. And then they do have a GUI so you can see the different clusters. Now they do have the ability to support a variety of instance types. They have x64 GPU, ARM. They do support placement policies and looking, they can do at least 200 gigabit per second over, and they do have InfiniBand available. They didn't have a lot of partner options on their web, so there probably are out there. I just wasn't able to look through their marketplace to find them easily focused on HPC. So there's lots of solid options across the cloud of resources, from campus resources to national resources to public cloud resources. And one of the things I wanted to throw out here is that there's so many options and so many choices that that there's a group, the Campus Research Consortium, Computing Consortium, and they have lots of mailing lists, lots of webinars and sessions where you can interact in meetings, and lots of different areas, from researcher facing, systems facing, to interest groups, to working groups, and then there's some of the operational groups to actually keep CARC flowing. Look to these resources if you need help, if you don't know where to go. There's a lot of opportunities for this to look at these various different offerings and also help navigate them. So I wanted to spend some time talking about Project Eureka, which is our follow-on to Cloudy Cluster. And one of the things that we wanted to do with Project Eureka is try to simplify some of that complexity and options for all these different things that we just talked about. And we wanted to do it in a way that could help people. And we're leveraging a lot of open source software, and we'll actually be making Project Eureka available without support to the R&D community. So they can use it, they can try it, and they can just keep using it into the future. Down the road, as we develop new things, we'll have some for-pay add-ons, but they'll be significant. But kind of the base functionality we're making available to everyone in the communities such as Internet 2, so you can really access this and navigate it and feel comfortable moving forward with it, even if there's tight budget years and those types of things. So I wanted to spend a little time on the vision and use cases. Kind of based on what we saw before, there's lots of options. And there's kind of three different classes of access modes, and they kind of overlap, but you have this interactive. I want to interact with something real time, be it visualization, be it some specific application for data and those types of things. So you kind of have this app interface. And then you have compute, which obviously interactive works with compute, but then you also have batch compute and scheduled compute and all those other things, and then storage, which is where we put the data that we started the talk about, and really how do you pull all those things together and from a project view, from a research project. And we really wanted to enable a multi-cloud edge architecture. We wanted to support very complex configurations while still hiding the configuration. We want to be able to support capabilities where you could launch your Project Eureka in any location. It could be on-prem in Kubernetes or in Google Cloud, Azure, AWS. You can launch it in any one of those. And then from that point, you can reach out and interact with other things that are not in that native cloud. All the solutions up to this point, and even Cloudy Cluster, you installed it in this cloud, or you installed it in this cloud, or you installed it on-prem, and it kind of stayed there, and some things kind of reached, but it really didn't give you the ability to install anywhere, integrate anywhere. And we had to build on some technologies to do that, such as Terraform and those types of things. But the goal here is to really provide that interface. And if you notice, when we're interfacing with Kubernetes, that enables NRP, which we kind of talked about earlier, or if you're integrating with Slurm, that provides access, pun intended. And then in the future, one of the things we kind of had to draw the line for the first version we're trying to get, there's things like HT Condor and Open Science Grid or OS Pool. We want to integrate with those things and continue to extend the capabilities in the future. And some of these, we leverage Terraform and other things to do the cloud integrations, but then we have layers that kind of provide an API programmatic interface for that. And in each one of these capabilities, there's kind of this functionality that we're trying to surface. When you're merging storage and compute, and you'll see an example of this later, but we really want to provide the capability to route jobs where they need to run. If you have a large data set sitting in Google, for whatever reason, a collaboration point, or AWS or somewhere, and you want to run a job there close to the data, you should be able to route a job and reference the data. If you have a little bit of data that you want to compute quickly on a regular basis and you can't get stuck in queues in your local system, you might run that to the cloud and then stage the data, and stage it back. If it's not too much data, if there's large amounts of data, I always like to say data has gravity, and you're going to go to it versus try to pull it to you, or you might, take forever. So here's a interactive application integration use case. So we've developed a project UI on top of Open On Demand, and then we have a Omni scheduler, which is kind of this meta scheduler concept that allows us to do all the cloud interactivity, and then we want to show how you can provision and run applications wherever you want to, and then the various different applications. So we'll show that in a minute. Now, one of the things we've really leveraged as part of this is Open On Demand. And Open On Demand is a really cool system that's used by hundreds and hundreds of HPC centers all over the world that allows you to provide interactive computation on top of your HPC cluster. And we started working with the Open On Demand team several years ago through a Science Gateways Community Institute, and we had a Cloudify program where we integrated it originally with Cloudy Cluster, and we liked that so much, liked how it worked, and that experience that, in Project Eureka, we actually continued and built some user interface capabilities for projects based on Open On Demand, and leverage that integration that we built on earlier. And one of the nice things about Open On Demand is the security architecture. And as we've kind of add this Eureka UI on top of Open On Demand's kind of per user Nginx process. So everything runs as the user to really prevent security issues with escalation and stuff like that. And we've kept that concept where you have these boundaries, like the scheduler is a boundary when you submit jobs that hands it over to something. And we're using, per user JWTs and other technologies to kind of integrate with Omni Scheduler, just like it would with any other scheduler. And how that works and interacts, we tried to stay pure to the open on demand model. And also from an identity perspective, the identity architectures, we're continuing to build this out. And I think I forgot to mention, this is a work in progress. So you'll see some demos. We're hoping to have a lot of this available this summer for people to start kicking the tires. And so we do want to integrate with the in-common system, like we did with Cloudy Cluster, Shibboleth, and we threw in, Omni Passkey as well. So you could do passwordless to this, Entra, Active Directory, OpenID, Connect, LDAP. So all of these types of capabilities, you need to be able to authenticate in a federated fashion to support research. So I wanted to give a little demo of how the interactive applications work. So let me hit refresh, make sure I don't have to log in again. And so this is a project-based user interface. And so I created a project called LLM training. And this one this home environment happens to be running in Google Cloud. We have it running in Google Cloud, AWS, and Kubernetes. We'll be adding Azure soon, kind of this core environment, and as the development progresses. And so you can go into each one of these projects and you can see applications that are running. So here's Jupyter, here's a desktop. So if I connect to Jupyter, it brings up a new tab. And then you can see that here's Jupyter Notebook, and it has access to my home directory. And so I can see everything that's going on and use Jupyter. And if I wanted to connect to the desktop, and there's the desktop, all in a web browser, all accessible. And that's a lot of what Open On Demand try to do. So we're building on that capability, and just kind of show you, if you go over here to Open On Demand, and this is the Open On Demand running at the same time, and we can look at the active jobs. And you can see, here's all the jobs that I have running in other instances and previous jobs. And so it is integrated with Open On Demand, just as it integrates with other schedulers through the Omni scheduler. And if you go back and look at the other project, we have 3 other instances running, and these are one-off instances running that application dedicated for that. And when you set those applications up, when you add a launcher, you have the ability to choose the applications, and different applications be configured per installation. Then you can choose the instance types you want, and then some other details, and give it a name and do that. So every time you launch it, you have that capability. And so we really look forward to providing this ease of use. And right now it kind of runs in that home environment now. And we just got the storage, which I'll show a little later, kind of reaching out. And you'll see that you can actually set configurations for locations of where you want these applications to run in different clouds or those types of things. But it's not something you have to choose every time. Within a project, which has, your users that you want to collaborate with, you have that ability. And so let's go back. So that's kind of the interactive application. And so I want to spend a little time talking about bursting and data staging. And bursting is this concept of, how do I go from here to there to compute if my data is, large, like I mentioned before, or those other types of things. So here's kind of a sample. You have Elastic on-prem to cloud use case. So let's say we have a on-prem is within the cloud. It's the on-prem cloud. And you have some jobs that you want to submit, and they could be submitted by various different mechanisms. And let's say you have your Omni scheduler running in Kubernetes, and then it's sitting right next to your HPC cluster that is kind of unchanged. It has Slurm there, and your compute nodes and your storage nodes. And the concept here is we want to give the ability for a job to have more intelligence, to know more of what it needs to do. And so let's say we have these different locations configured. Within a job, we can say, hey, I want this job to run in Google Cloud or AWS or Azure. And what happens is when it's sent to OmniScheduler, we actually have API integration with TerraSpace Terraform that will dynamically spin up the resources needed. Now, the resources might be Elastic Scratch because you want to transfer, small to medium amount of data there for all the nodes to access. Then you want to transfer the data over there. And then you want to run the compute. And then when it's done, you want to, stop the compute node, stage the data back, and then, delete the file system. You got to do things in the right order. You might end up with nothing. And that ability to stage to and from your on-prem cluster or to other places, is something that we've been asked over and over again. People really want this in a consistent way that's easy to interface for the users. And so to kind of achieve that, in Cloudy Cluster, we had the Metascheduler. It's the first place where we kind of developed the Metascheduler concept. And when you added job directives to your HPC job, it kind of made it cloud enabled. So you could have an HPC job that could be configured for AWS and Google. So we had GCP, you could add instance type, image ID, you could do use preemptible in AWS, you could use Spot, you could switch the network capacity, you could also do the tier 1 capacity in Google Cloud. So basically, by adding these job directives to the job script, which we want to make easy for people to add, know what they are, and not have to memorize everything. But once you have that set up, it'll go. And so if you have that concept of if your job has information configured, say, hey, I want to route this to this location, which is AWS, and then it spins up that, runs it, stages the data back and forth as needed. But a lot of your jobs will just flow through unharmed or unmodified to your normal HPC cluster. So this is something you can put in without having to radically change things. Now, in Project Eureka, because of the diversity of all the different locations that we're accessing, we kind of are changing the directives a little bit, making them a little more compound. But the concept's still the same, where here's your compute, I want some storage, I want to spin up these storage nodes for this job. But we're also adding the concept of transfer. And this is some of the stuff we're working on now, so this will evolve a little bit. We're really going to have, as part of the job operation, I want to spin up the nodes I need, I want to transfer the data I need, and then when I'm done, I want to transfer the results, and I want to clean it all out. And we want to try to have as close to a zero footprint in the various clouds as possible. Because we learned with Cloudy Cluster, if you use the cloud every once in a while, you have to have resources running there. There's that bill that, keeps coming up. And it's really, we feel better to kind of, if you're going to burst, to really burst. And there's some interesting projects we worked on, various different things, like with the Tapas group, where they dynamically spun stuff up using Cloudy Cluster that really made sense and we learned from. So kind of as we're moving towards the storage location, I wanted to give a little demo of our storage manager, which is also part of the UI. So we have our Lost in Deep Space project here again. And if you notice, there's only one storage location. That's the project storage. Obviously, I have my home directory storage, but let's say I want to create a managed bucket. Let's say call it I2, and it has to be unique. This one's running in Google, so this is the home environment. It'll automatically create it in the Google project where this is running. And so we'll save that, and that'll happen, and it'll take a sec for that to provision. I also, let's add an external bucket. And this is stuff that's just kind of pulled together, but here's a Google Cloud. This is one of our gcp.cloudycluster.com website. It's public bucket, so we're not going to, it's already public, so we're not going to give anything away by doing that. You paste the URL in there, It automatically determines everything, and this will be read-only, so you don't need a key. And then, why not? Let's just grab the AWS version. So this is off running in AWS. And we'll create another external bucket, paste this in, parses everything out right, save it. So while those are thinking, let's go back to my LLM ones, which we already have some previously configured ones, and click on the storage manager. And if you notice here, each one of these locations here is a different storage location. So I have my home directory, which I've already copied some stuff into. Here's the GCP read-only bucket, the AWS read-only bucket. We want to get some identifiers on there so people can tell. And here's the project storage, which only has a couple of JPEGs in it. And the concept here is these resources are not only available to this storage manager, but these resources will be available to each of the HPC jobs. So you can specify these to get data. All the keys are managed and everything through that. So you can pull out the data that's needed. And so you can do things like I'm going to, drag and drop this. You can also drag and drop subtrees. And we've actually developed what we call OCP or OmniCopy, which is like a multi-point data staging. So all these different points invoke code that move the bytes between those different things. So it can be enabled from this GUI, but it also can be enabled from the Omni scheduler for the applications and also for the jobs as they run. So, you have that ability to do things, look at stuff, expand, and we'll continue to work on the usability. But the concept here is it's very fast, and moves the things that are needed. And we'll also be adding the capabilities to do data staging jobs. If you need to, a job to run regularly to stage data, those types of things, those will all be able to be configured. So that's kind of, where we come back from the storage manager. So with that, I thought that it might be good to, thank you for your time. If you have questions or ideas, we really like feedback. If you like being guinea pigs when we're ready, let us know. Again, you can run this aside or you can run this in the cloud to try things out. But we really want to make this a community effort. But thank you.
Great, thanks, Boyd. I'm sorry about the video. You might want to try it now at the end of your talk. If you could still turn that on, I think you can, or you might not be for some reason.
It still says no, but okay.
Oh
maybe
no, you've been foiled. So yes, thanks again. And if anybody has any questions, please feel free to put it in the question and answer. We do have one so far. How can you manage costs and optimize and costs with this project as a question that we have?
Yeah, well, one of the things that we did in Cloudy Cluster that we want to bring forward, and then we want to extend on that, is you actually can put hints in your jobs as well, and I didn't highlight this on that slide, that actually goes into the billing console. So it tracks who runs what, so you can go into the billing console in the various clouds and you can see who's running. And then you can also have a project code, so you can put projects, so when it gets to billing, you can see that. The things we want to add in the future with Project Eureka is the ability to put in an amount and say, hey, don't let me submit jobs, or don't let my students submit jobs if we get this close to this limit within a project. So we do want to put in some kind of guardrails at the project level to prevent people from running stuff. There may be ways to stop things if they're running, because things can get very expensive if you're doing some, LLM training or AI type work with a lot of GPUs. We're hesitant to probably delete data. Just because, hopefully we give a percentage before, you'll see you're getting close, and then you can move data, but we don't want to automatically delete the Nobel Prize type of thing.
Again, if you have questions, please feel free to put it in chat or in the Q&A box. So Boyd, I guess maybe one question that I had for you was Project Eureka is currently in the working stages. Do you have a timeline of what that looks like and when that might be available for the community to try out?
Yeah, we're hoping to get ready for early access sometime this summer. It's one of those, it's a development project. We still have some work to do, but we're still hopeful for, July or August. We can let people start kicking the tires and trying it out, in a test environment.
Here. Are there more questions for Boyd? So Boyd, maybe one question that I have for you while we're waiting for people to gather their thoughts perhaps is the evolution from from Cloudy Cluster to Project Eureka. Can you walk us through a little bit of what that evolution has looked like, and is it much easier for people to use the templates now, and how that evolution has gone? Is this something that you can update us on?
Yeah, there's kind of two components of that. When we developed Cloudy Cluster, in some ways we made it a little too easy and we restricted it. Not from a user perspective, but more from a system administrator perspective, where it did things very well. But if you wanted to connect to your on-prem network, or if you wanted to connect to things outside of Cloudy Cluster, it was much more difficult. And we learned that there's a lot of special cases where people wanted to do things, and people really wanted that connectivity. So from an administrator perspective, there's more options, so there's more complexity. But we hope to continue to make that easier, and hopefully someday we'll have a spin up a test version very easy like we did with Cloudy Cluster, but it won't have the flexibility that the other has. Now, from a user perspective, we hope we're going to keep it the same. So if you run a small little deployment environment, that once you get your job configured, it runs, it'll move the data. So we're hoping we've made it easier for the researcher and the research team through this process. So that's the two sides of that coin.
Great, thank you. Are there questions for Boyd? And Boyd, I believe that you will be working with us at Internet 2 to run a Project Eureka hands-on workshop when it's finally out for the community to use.
Yes, yes.
That will be sometime. Yeah, so I just wanted to put that out there for the audience that Boyd will be returning to Internet 2 to help us run a workshop once Project Eureka is out. It would be sometime in the July to August timeframe. So if there are interest, keep your eyes peeled. And also, feel free to reach out to Boyd if you wanted to give this a try before it's released.
Yeah. Or if you have ideas or input, or want to know if a use case is covered. A lot of that information is helpful. It's like, hey, I've got this crazy use case, that's really baffling. So we, at this stage of the game, we actually like those kinds of conversations, because sometimes it's easier to squeeze those in through the development cycle.
Great. Okay. Great. I think, there's another question about whether there's access to the slides. So.
Yes, I'll send the link to you and you can share it, Amanda.
Fantastic. Okay, great. And if there are no more questions for Boyd, thank you so much, Boyd. We'll see you again soon at some point.
Yeah.
Hopefully
thank
with
you
the
so much.
time. All right.
Everybody.
Thank you. Thank you, everybody. Bye-bye.
Take care. Have a great one. Bye.